Check it out now, y'all.
NanoHub U, online instruction.
Hi, welcome back. We're going to, the next 3 lectures, we're going to cover some experiments that were performed in the late 1800s, early 1900s that were pivotal in launching this quantum mechanical understanding of matter. If you've listened to the previous 2 lectures, you'll remember we've discussed we conducted a very quick review of mechanics of particles. And we tried to contrast the mechanics of particles with the nature of waves. We discussed the wave equation. We also discussed Maxwell's electromagnetic waves, and we paid specific attention to the energy that's transported by an electromagnetic wave, because it turns out that feature of Maxwell's theory is very relevant to the discussion that we're going to conduct in this lecture. So we're going to begin by talking about 2 very classic experiments. One is referred to as Blackbody Radiation, and the other is referred to as the Photoelectric Effect. Both these experiments deal with the nature of electromagnetic radiation, and we're going to try to highlight the difficulties that were encountered when the experimental data from these experiments were attempted to be explained. So let's begin with blackbody radiation. This is a topic that's enjoyed attention for a number of years. The earliest work dates back to the 1850s, and the work continued all the way up. Well, it still continues today, but the seminal work continued up into the 1890s. And the reason blackbody radiation is kind of interesting is because it combines thermodynamics with electricity and magnetism. And the premise is pretty clear. Everyone knows that if you heat up an object, if you get it hot enough, it starts to glow. It acquires a characteristic color. And the question is, where does that light come from, and what's the nature of the light that's emitted from a hot object? That was not at all clear in the middle of the 1800s. The experimental results started to come in, and the first important result is Stefan's law that was published in 1879. The idea was you take an oven, you heat it up, and then the cavity inside the oven gets hot enough it starts to emit radiation. If you then punch a little hole in the oven, and if the hole has a cross-sectional area A, you can then extract some of the radiation from inside the oven, and you can start to measure the intensity of that radiation, or the power that's emitted from the oven as a function of the temperature T that the oven is held at. So T here, that's the parameter that you're going to adjust experimentally. And what you're going to do is you're going to set a detector up over here, right? And you're going to use that detector to measure the radiation that comes out. Well, Stefan did these measurements, and he found that the power that's emitted is proportional to the area A that's punched in the hole in the side of the oven, and it also is proportional to the 4th power of the temperature T that the oven is held at. So this T to the 4th behavior is very characteristic of blackbody radiation, and it's certainly valid whenever the temperature of the oven is much greater than room temperature. Further refinements turn this proportionality between power and the 4th power of the temperature into an equation. So 2 parameters were introduced. One is referred to as the emissivity of the object. This tells you something about the nature of the surface from which the radiation is emitting. Sigma is known as Stefan's constant. This is a value that's obtained from very careful measurements of power versus temperature. So this was the state of the situation in 1879. The subject was advanced significantly in 1895 when Wien and Lummer actually measured the power as a function of wavelength that emitted from the oven. So they did spectral measurements, and again, the measurements were very similar to what Stefan did. It's just that by 1895, they had good power meters that they could use to measure the intensity that's coming out of the oven as a function of wavelength. The idea is pretty simple. It goes back to our discussion in the previous lecture. If you collect radiation for an amount of time delta t, then the length that radiation travels is just the speed of light c times the time interval delta t. If you know the cross-sectional area A that you've pushed inside the side of the oven, right, then you can define a volume delta V, right? And this volume delta V is this area A times this length C times delta T. So the intensity that passes through the oven at a particular wavelength can be converted to an energy U, right, using this equation. And this energy U is ultimately related to the energy density that's contained in the inside the oven. So by measuring the intensity I, you can work backwards and get an expression for this U total, and then U total is something that you can calculate using Maxwell's theory. So that's the idea. You're going to make this measurement as a function of frequency, or as a function of wavelength, to try to understand the spectral character of the light that's emitted. Well, this slide summarizes basically what was discovered, right? What was learned was that the light that's emitted from a black body is continuous. It has no well-defined emission lines. It seems that the light comes out at all wavelengths. The light spectrum does not depend on the material that is heated to the first approximation. It only depends on the absolute temperature T. And the energy density of the radiation field that's emitted seems to be in equilibrium with the temperature of the heated object. So this is how thermodynamics comes into the problem. So this is how you're going to try and calculate this energy density from thermodynamics and Maxwell's equations. You're going to compare that result to what you measure experimentally. The character of the spectral radiation that's emitted is illustrated very nicely in this application that can be accessed for free on the web. So I give the website down here, so you're free to go look at that. This application is nice because it allows you to adjust the temperature of the emitting object, and then it gives you a plot, right, of how that intensity varies as a function of wavelength of the emitted light. There's a narrow region here that's indicated by these colored bars. This is the visible region of the electromagnetic spectrum. And when you start to see a hot object emit radiation, it's because there's a significant amount of radiation in this visible region of the electromagnetic spectrum. So it's a useful application to investigate on your own, and I encourage you to take a look at that, because it'll really complete your understanding of this topic. So what's going on? Well, Rayleigh came up with an explanation in 1900, and Rayleigh's explanation was that there are charges, presumably in the walls of the oven, and these charges are jiggled back and forth as the temperature is increased. And of course, anytime you've got a charge that's accelerated, that charge will emit electromagnetic radiation. So all these so-called atomic oscillators in the surfaces of the oven will start to emit radiation at different wavelengths. And those wavelengths of radiation will fill the inside of the cavity, and then when you punch a hole in the side of the cavity, you sample all the wavelengths that have been generated inside the oven. The argument is that many of these wavelengths will not persist over time simply because the electric fields that are produced by these electromagnetic waves do not vanish at the surfaces of the oven, okay, so inside the cavity. So the idea is that only those modes or only those wavelengths such that there's an integer multiple of wavelengths that span the inner dimensions of the cavity, only those guys will persist, right? Any mode that happens to have a non-zero value for the electric field at the surface of the oven, that'll get quickly damped out, and you won't observe that experimentally. So following that line of thought, it was possible then to predict what the emitted intensity as a function of wavelength should look like, and that's indicated by this orange-colored curve here. This is the classical prediction based on a calculation of the radiation field inside of a cavity, and it assumes that the electromagnetic radiation forms these standing waves. So this is referred to as the Rayleigh-Jeans theory, and if you try to compare the predictions of the Rayleigh-Jeans theory to what was experimentally measured, you'll see that there's really not very good agreement at all. At large wavelengths, the results tend to overlap. The Rayleigh-Jeans does in fact fit the experimental observations for long wavelengths in the infrared. But as you move into the visible region of the electromagnetic spectrum and also into the ultraviolet region of the electromagnetic spectrum, there's more and more modes that can fit inside this cavity, so the intensity should continue to go up, and of course it doesn't experimentally. So there's a serious problem with this theory. To overcome this problem, Max Planck in 1900 made a remarkable hypothesis. Rather than consider the light inside the cavity as standing modes of the cavity that were determined by the dimensions of the cavity, he said that maybe these atomic oscillators that emit radiation, maybe those atomic oscillators emit light which is quantized in energy, and he quantized the energy of the light by his famous equation, which says the energy of this quantized light is equal to some constant h, which is now known as Planck's constant. This is adjustable and comes from the experiment, right, times the frequency f of the light that's emitted by the atomic oscillators. So in order to fit the experimental data, you get a value for Planck's constant that's 6.6 times 10 to the minus 34 joules seconds. And this is a number that we're going to use continually throughout the semester. What Planck was able to derive, actually, he cooked it up, right? He cooked up a function that was able to predict the measured experiments, and the function that he cooked up to fit the measured experiments is shown in this equation here. This is basically the energy density in a narrow range of frequencies df. Right, and it turns out that when you integrate that energy density and over all frequencies, you then recover the t to the fourth law that Stefan measured. So this was a radical hypothesis, because up until this point in time, the energy in an electromagnetic wave was considered to be continuous. It just depended on the amplitude of the electromagnetic wave, and this is what we've got sketched in this slide, right? This is what we went through in the last lecture, right? The average intensity in an electromagnetic wave is proportional to the square of the electric field, and by adjusting the amplitude of the electromagnetic wave, right, you can get any value for the intensity out of the electromagnetic wave that you want. So nowhere in this discussion from the previous lecture does this frequency f appear, and nowhere in this discussion is there a suggestion that the energy contained in an electromagnetic wave is quantized. right? This is something that that Planck assumed, and when Planck assumed it, made these assumptions and followed through the arguments in a logical way, he was able to explain the experimental data very accurately. So there had to be some fundamental correct assumptions based on his theory that were being missed somehow, right, in this classical theory for the electromagnetic wave. So, you know, maybe if that's the only experiment that's difficult to explain, maybe you know, it's just a lack of understanding of a particular detail in the theory. But that wasn't the case, right? There were other experiments that involved the interaction of light with matter that also were virtually impossible to explain using these classical models for electromagnetic fields. And the next experiment I like to talk about is the photoelectric effect. And this is an experiment that was done in the late 1800s. It produced a surprising result. And what it basically did is it produced an electron current from light. And the way the experiment works is you have a source of light, you illuminate a target, a metal target with that light, and then you collect electrons that are ejected from the metal target. These electrons form a current. And what you can do experimentally is you can investigate this and you can start to lay out what depends on how the ejected current, how the photocurrent depends on, for instance, the intensity of the light, how it depends on the frequency of the light, which basically means the color, right? There's an issue about the composition of the target. You have to worry about whether the target is made out of copper, silver, gold, so on and so forth. You can investigate the energy of the electrons that are ejected. And then lastly, you can also measure the number, the electron current that's ejected. And you like to believe that you could explain all this data collected from these experiments using Maxwell's theory of electromagnetic radiation. So again, if you really want to understand the experiment, there's a nice simulation on the web. I give the website here. I encourage you to go look at this on your own time. In this simulation, you can adjust all of these parameters that I just mentioned, and you can start to see the influence that these various parameters have on the ejected photocurrent. So, what sort of results might you expect based on Maxwell's theory of electromagnetic radiation? Well, if you focus on monochromatic light, that means light with a fixed wavelength. Okay, so only light with a specific wavelength illuminates the target. You would expect, based on Maxwell, that as the intensity of that light increases, the maximum energy of ejected electrons should also increase. And this just follows because the intensity is telling you the energy that you're depositing into the target. And as the intensity increases, you deposit more energy, and that increase in energy should then be somehow distributed into the energy of the ejected electrons. So you would expect the maximum energy of ejected electrons should increase without bound, actually, as the intensity of the electromagnetic radiation increases. You would also expect that for a given wavelength of light, if you have very low intensities, right, maybe there would be a time delay in electron emission, because if the intensity of the electromagnetic radiation is small enough, you have to wait a certain length of time for the electrons to acquire sufficient energy to be ejected from the metal surface. So for very low intensities of light, maybe there's a time delay that you can measure and experimentally determine that time delay, and that would then tell you something about how the electrons inside the metal are accumulating energy, right? And then lastly, another important prediction is that electrons should be emitted for all wavelengths of light. So for any color that you choose, right, if you either put on sufficient intensity or if you wait a long enough period of time, electrons should be ejected. And all these predictions are reasonably clear, right? There's very little that you can argue with if you believe Maxwell's theory for electromagnetic radiation is true. The sad story is that experimentally none of these predictions were observed, right? So all the experimental results collected from all over the world contradicted these predictions that were reasonably well established. So what's going on? Well, it took Einstein in 1905. He came up with the theory of photoemission, and it's still the accepted theory today. And his theory of photoemission was able to explain all the experimental data. And I like to go through that theory using this schematic diagram to illustrate the various features. So to begin with, if we have, let's say, a metal surface, and we illuminate that metal surface with light, right, we're going to assume that the light incident on the metal surface is monochromatic. That means it has has a fixed wavelength, okay? Only one wavelength of light illuminates the metal surface. All the action, all the electron emission occurs right at the surface of the metal. So some of the light that comes in is, of course, reflected. That light we're not interested in. Some of the light that comes in actually penetrates into the metal, and it's that light that penetrates into the metal that causes the photoemission process. Within a very short distance of the metal surface, right, the light is absorbed, and Einstein says the light is absorbed by an electron. So all the physics that occurs is within, let's say, a fraction of a wavelength of the electromagnetic radiation inside the metal surface. And to understand that process, it's useful to use this simple diagram, right? So this represents the metal, this represents the vacuum, this is the region outside the metal surface. This distance here is going to be on the order of the wavelength of the incident electromagnetic radiation. And what these black dots represent is these black dots represent electrons which have different energies that are trapped inside the metal. And these electrons are trapped inside the metal by a barrier, right? Very similar to the barriers that we're going to talk about later in the semester, right? And this barrier has a certain height which separates the vacuum level, which is up here, right, from the most energetic electron, which is down here, right? And this barrier height is referred to as the work function, and that work function is given the symbol capital W, or very often it's given the symbol phi, right? So the electrons don't spill out from the metal into the vacuum. So if you take a piece of metal and you wonder why electrons don't spill out of the metal into the vacuum, it's because they're held in by this work function barrier. Okay? So what Einstein had to do was he had to hypothesize that the incident light was comprised of photons. These are quantized packets of energy, very similar to the quantized packets of energy that Planck had to assume to explain blackbody radiation. The energy of each photon is equal to the Planck's constant h times the frequency f of the photon. So Einstein took exactly the same formula that Planck had derived, and he applied it to this photoelectric effect. The idea is that each photon comes in. If it penetrates into the metal surface, it has a probability of interacting with an electron. If it interacts with an electron, it is possible that that photon will completely disappear and in the process give its entire energy to the electron. The electron on this diagram would then change from some initial energy down here to some final energy up here. And the height of this vertical transition is just the photon energy, HF. If this final state electron has an energy that overcomes this barrier, this work function barrier phi, then that electron can escape into the metal, or escape from the metal into the vacuum. And out here, once it's in the vacuum level, we can measure its kinetic energy, and the kinetic energy is represented on this diagram by the difference between this vacuum level line and the energy of the electron after it's been photoexcited. So you can start to see how this simple models explains a lot of the experimental data, right? If the photon energy is sufficiently small, right, the excited electrons will never clear this work function barrier, so they'll get excited up and then just fall back down into this collection of electrons. It doesn't matter how much intensity or how many photons per second you pump into the metal, if the photon energy is just small enough, irrespective of the intensity of the light, you'll never get electrons to be ejected. You can also start to predict the maximum kinetic energy of the electron. It's just going to be equal to the photon energy HF minus this work function W, right? So you can start to understand the kinetic energies of these electrons in terms of the work function properties of your metal target. So this theory was wildly successful. It was kind of revolutionary because it threw out a lot of the assumptions based on Maxwell's equations. But it did in fact explain all the experimental data, and this is actually what Einstein got the Nobel Prize for about 20 years later, his explanation of the photoelectric effect. So this is a quick summary of two seminal experiments performed in the late 1800s, early 1900s. In our next lecture, we're going to look at two other experiments and see how they also reinforce this idea of quantized photon energies in electromagnetic radiation. So we'll see you for the next lecture. Thank you.